Last. Okay. So today morning when we had the big data panel, there was some discussion. Very first initial discussion was about Hadoop and Spark, if you remember. And many of you may not have.
He needs to switch his mic back on. You're trying to.
Is it okay now?
Yeah.
Okay, sorry. Yeah. So when we had this discussion, the panelists, some of you may have the context, but many of you may not aware. So I would like to just take a poll that how many of you are aware about Apache Spark? Okay, so good number of you are aware about. So I will be giving just much more orientation toward that big data stack, the BIDA stack, and particularly in Apache Spark, and how we came across and why we are using it. So as in the introduction said, I am currently principal technologist at GAWAS, and GAWAS provides a big data platform for operational intelligence, and we deal with very huge high volume telco use cases. Earlier Eric Carr presented hundreds of billions of transactions per day in some customer settings. So that's and it's we early on latched on to Hadoop a few years back, and so we have a lot of experience in the big data, but more and more now use cases coming in that also requires near real-time processing, and additionally additional models of interaction like interactive queries, the fast queries, etc. So that's where we were looking into the stacks, so we compare the Storm and Spark and settle down on the Spark. So in that context I will be covering, but mostly this presentation is not related to how we are doing, what we are doing at GAWAS, but what that Apache Spark stack is and some of the underpinnings under the hood. And my co-speaker just immediately after me, he is from AMS Lab. AMS Lab is where the Apache Spark was one of the project in the BIDAS, and so that's where it started, and then it open source, and now it is in Apache, and it has a rapid momentum. It started just 1.5 years back. It got into the Apache incubation, and it is one of the fastest program over there, and it graduated from the incubation I think within 6 months, and now it will be 1.0 release. So it's a very fast in that set. Okay, so there are the key three things are there, that what we see is that it's a fast, it's easy to use, and the third factor is also very important, that it mixes 3 different programming paradigms that is of interest. Some of these slides are influenced and coming out of the original presentations from AMS Lab, so I give attribute to them. Just to maintain the clarity of the message, I kept some of the content like that. So the history, you have seen that when we started with Google publishing this HDFS, GDFS related paper, and that MapReduce related paper, then it took the Hadoop. Over a period of time, it kept use cases grew, and then there are a lot of ecosystem got developed. But similarly, later on, Google published another paper like a Dremel and then Peggle that influenced Impala, and Drill is another open source which is contributed by MapReduce, MapR into the Apache, and so that is one path. Then in the streaming processing, Twitter started with the Storm, and then similarly there is a S4 that got contributed from Yahoo. So there are a lot of these movements are happening to solve the big data problem in the different contexts. One of the paradigm is related to how to make it a faster interactive query. Another was that how to deal with the huge big continuous stream of events or the stream of data. The third is that it could be interactive programming or the iterative programming, the graphs type of processing. So there are different, these paradigms are there, but each one of them got solved in a very different way, And Hadoop stack, on top of that, whenever we have some implementation, it carried forward whatever the limitations that Hadoop has. So AMSLab took a very innovative approach, in my understanding, is to put all these pieces together in a very cohesive way. So that gives the benefit, much more easier programming, the faster programming, the performance also is faster. So we'll go through that. So these are the three interaction models which are much more common. One is that the MapReduce, which is a batch-centric processing. Then another is the streaming, which is a continuous event processing that initially CEP was a use case, but distributed stream processing. And the third is interactive, the interactive query, both from the data scientist point of view or ad hoc queries. So that's the third paradigm. That's a very common. So in this case, what we see is that different programming models and different tools to solve that. So that's where the Spark became very much important. Okay. So just to capture what the Spark is, it's open source from AMSLab. It is actually giving, as I said, the fast processing. There are two important aspects is that now the question comes with that what is the relationship with Hadoop, and whether it is a competitive or it is a complementary technology. So it can be looked at in a both way. It can be looked at in a way that it is a complementary, because it is in the Hadoop stack there are two important aspects. One is the storage, that is the HDFS, and another is the programming, the distributed computing framework, which is MapReduce. So Spark does use or supports HDFS, so that way it does complements into that. But it has implemented its own MapReduce framework, which is much more faster. It supports iterative programming. It supports in-memory computation in between the job. You can share the some of the process results that can be shared across. So that way, it is and also it is optimized, because the developers from the Spark looked at how the processing is typically done and how we can optimize the jobs. So if there is whenever there is a say, we have map and reduce, or in that case, if you are not really needing to do the shuffling of the keys, if the processing can be happening within the same job, then it doesn't really do the shuffling. So that way it is the scheduler is a much more smart scheduler. And that's the one advantage, that there are similar a lot of optimization has been added, which understand the processing cycle or the DAG nature of the jobs itself. So Spark history is that I briefly covered that, but it's essentially what we are seeing is that it's a great momentum is there. There are a lot of companies which are jumping into that. Initially, there is a rare combination of academic research and industry. Initially, the project came off the academic setting, but there are companies like Yahoo is actively contributing to that. Then Databricks is a commercial company behind that. Then Cloudera has added Apache Spark into CDH4 and getting into CDH5. So in future they will be adding probably streaming also. So right now Spark Core is part of the Cloudera itself. And then just last week Mapper also introduced Apache Spark into their stack. So you can see that the more and more companies which are providing the pure big data platforms, they are adding Spark as a component. Hortonworks hasn't yet added it, but we may see in future. Hortonworks has another technologies in a stack which to make it faster, particularly Tej for the interactive queries. But streaming is another paradigm that they need to solve, and currently they are supporting Storm into their stack. But who knows, in future we can see Hortonworks also getting a Spark into their stack. So these are the various companies over there. So why Hadoop is particularly we are seeing the performance problem is that the way the job gets launched, every job is actually new process get created. And in between jobs, what happens, right? Typically, when we do the big data processing, it's not just a one job. We may parse certain, say, first results, and then second iteration on top of that could be the aggregation. Third result of that could be some clustering. So when you have the iterative type of processing, it requires multiple jobs, and in typically Hadoop stack, it would result into that you get that the result into serialize, and they need to be persisted so that the next job can be picked up, and so it gets stored into the file system. So there is a disk I/O involved. So that's and also the life cycle of the job itself, because the job is nothing but just launching a process, and that itself again is a costly affair. So it can never be in terms of minutes. Or rather, it is seconds, and if you want to get latency which is much more lower than, it is a problem for the map reduce in the Hadoop case. So in case of Spark, what does it do? It supports a caching in between the job. So that, and also it supports the optimization, so there is no unnecessarily shuffling is happening. When you can, there is just a map and the same keys are happening, so you don't have to basically shuffle the queries. So that way, it's claimed that the performance is 10 times to 100 times, which is all based on the use cases. This is the performance numbers from the AMS lab, which can basically show that it is a much more faster. We did our own simpler, we can see the worst case versus the best case, right? The results that quoted from the AMS lab are much more on the best case scenarios, because the use case gets selected. Typically, it could be where the iterative programming is involved. For example, page RAM algorithm. So there are multiple steps to solve that problem. As a result of that, Hadoop based, it is definitely is a slower. We did something which is a very the basic benchmarking. Just our current implementation, one of our application converted into from Hadoop to Spark, and immediately we saw performance boost up to the five times without doing really any kind of hardware tuning or any other extra tuning. And it is just a conversion of the existing job itself. So that gives a one confidence. When we say that the performance, it really results into huge savings. For example, that performance benefit actually impact the reduction of the hardware itself. So that is when the iterative programming is not really involved, but still you can get a huge benefit by doing the same type of a map reduce programming, but on top of Spark. So now there was another discussion today morning was that badass stack, which is a Berkeley data access stack. So which typically you can see that the HDFS, then the clustering support that you need, it could be Mesos, it could be Yarn. On top of that, the Spark framework, the Spark engine itself. Then there are multiple things. One is the Spark streaming, which is a component which supports the engine supports the streaming use cases. Then there is a Shark, which is to support the SQL SQL-like queries, which is Hive compliant, so that's queries. Then GraphX for the graph processing, machine learning, ML-based library, and then there is a BlinkDB, which Samir is going to cover. Okay, so some basic paradigm why we get some benefit in Spark. So one of the things is called as a resilience data set or the RDD. So which is a immutable collection. It is a distributed parallelized collection, and it supports since it is a immutable, and there is a very interesting framework that is used in the RDD. Which is a lineage tracking. So based on the immutability and lineage tracking, it can support fault tolerance. And I will give the example. When we start with some say data source, we got some collection, and we transform into the second one. We got some, say, let's say that some data set, and we computed only a certain part of the results. Say if you are doing frequency counting, and we did the processing, we got the first set of the numbers aggregated, and then we are doing the next processing is that getting the top n. So out of that, so if you are getting the ordering and top n, so we are doing certain steps in that processing. Let's say that the job crashes. So in this process, what happens is that every RDD from one to another is linked, and that linkage is actually tracked by the framework itself. So when it crashes, it can recreate as long as you can recreate the original one. So that is the precondition. So once you have the original data block that you can start the processing, you can get the benefit of the fault tolerance itself. So that's one important aspect. So this is the example that it gives. It goes through the multiple steps, but if it crashes, you can get what. If there are a lot of steps, then of course it will be slower to recreate everything. So there is a checkpointing also there, but the interesting concept is the lineage tracking itself. Another interesting aspect is that Arun Murthy had mentioned, right, a big simple hammer. But this big simple hammer, which is just a map and reduce paradigm, has caused a lot of responsibility on the shoulders of the programmers. So there are common patterns that we all implement, and those patterns, whether it's a filtering, joining, splitting, then collecting, aggregating, mapping by keys, reducing, all these different paradigms, which are in case of Spark, they are provided as a part of the framework, and they not only they are the programming construct, but under the hood implementation is much more faster. So it gives the fast performance, as well as it gives much more faster results also. So I will just give some of the programming construct. Another thing that it provides interactive shell, which is the Scala based shell. You can use it, or you can also use the Python for the interactive programming. And then this is just an example that this hello world typically for in case of big data is called as a word count. So in simple couple of 3 lines, you can just write that program and you can run that. So it shows that the whole power behind the interactive shell as well as the programming. Of course, a lot of credit goes to the Scala itself. Scala is much more concise and very powerful functional language for that. Another aspect is the streaming. So one difference between the Spark streaming versus Storm. Storm is much more discrete. Every event get separately processed, as against Spark streaming implemented micro batches. So batches can be tuned to say 500 milliseconds, and they can be processed so that you can get the latency or the performance as low as in seconds. By making that micro batches, actually it brings the programming model close to the MapReduce itself. So that's another benefit of the programming model itself. The second aspect is that it also helps into implementing the fault tolerance and the recovery. So that's the 2 benefits of the Spark streaming itself. These are the some comparisons. These are the early comparisons that came from AMS lab. So you can see that Storm versus Spark streaming is almost 5 times performance difference over there, and S4 is way below the radar in that. These are the data sources which are already implemented, and you can integrate with other sources. These are some of the transformation models. I will skip the programming, but the Shark is the Hive query, and Shark provides optimized way. It has internal in-memory columnar type storage, the caching. So that becomes is a faster. It also, compared to Hive, there is a underneath, Hive is on top of MapReduce. So every Hive query is actually get translated into MapReduce job, just like a pig also does the same thing. So it's inherently slow, but in case of Spark, since it is based on the Spark platform itself, and additionally it has in-memory caching, it is a faster. So you just keep this. This is the performance results that just to compare the query itself. You see that here the Impala and Shark, they are almost comparable, at least in the some setting. And but when the number of iteration goes very high, at that time Shark takes over Impala. So that's the one observation you can see from this number. So overall message is that Spark and Spark streaming Shark is a faster. It combines all the programming models, 3 programming models, at least the interaction model, and it also provides the easier programming with the Scala, lot of out of the box constructs, and it's very optimized. Another component, it has a ML base. Those who are coming from the machine learning, Spark, the BIDA stars itself provides the whole framework for the machine learning. There are these out-of-the-box implementation of algorithms, from the regression algorithms to clustering algorithms, classification algorithms, likewise. So I would be concluding this, and then Samir would cover the BlinkDB. So most of this, the rest of the presentation would be around Samir's BlinkDB. We are not taking questions now, right? We are taking. Yeah. We'll take the questions later, and right?
A lot of question and answers after both the sessions. So till Samir is setting up his laptop there, I'm sure you just heard about BlinkDB in Kandoraj's talk. And we have all this big data, right? We have tons of data, huge volumes of data. And what if we cannot get to that data very fast? If it is taking big time to get to that data, it's a big headache. So BlinkDB is one of the tools or technologies that addresses that concerns. It is basically works on a parallel queries on a very large amount of data and gets the response very fast within certain approximations. So Samir Agarwal is going to talk about it. Samir is BTech from IIT. He's a gold medalist, President's gold medalist from IIT, and he has been doing his research at AMP Labs in UC Berkeley, where he's doing his PhD. And we are fortunate to have him here because he is the designer and leading the effort in BlinkDB. So I'll welcome Samir. Thank you.
Thanks a lot. So good afternoon, everyone. My name is Samir, and today I'll be talking about BlinkDB. BlinkDB is an interactive query processing framework that supports approximate queries on very large data. So with Spark, Shark, and like other in-memory query processing frameworks, or kind of like in-memory processing frameworks, really pushing the limits of in-memory computations or interactive queries, the next question that comes to mind is as to if we can do better than in-memory. And being better than in-memory can mean one of the two things. First of all, can we actually get more for less? Which is to say that can we actually get the same quality of answers that we get now with using fraction of resources. So I mean, let's say that we right now use 100 machines and it takes 10 minutes to get some answer. Can we use 10 machines, or can we just use 1 machine to get the same quality of answer using the same time? And then the next question is, can fast actually get even more faster? So right now, in-memory computation, right? I mean, it's pushing the limits. It's what used to be computations that used to take hours and hours now have been pushed to probably minutes or sometimes tens of seconds. Can we get even better? Can we get this latency down to seconds, or can we actually get this latency down to milliseconds? And that is the question that we wanted to ask. So just to give a brief intuition of the time scales that we are talking about, let's pick a simple query. think of it as a very, very simple query. In this case, this query was just calculating percentiles, 99 percentiles on 10 terabytes of data that was spread across 100 machines. So if this data is now spread across hard disks, and we're using some cluster computing processing frameworks such as, let's say, Hadoop, it takes around half an hour to 1 hour to process this data. A majority of the time is spent in reading this data. Disk bandwidths are of the order of like 100 to 200 Mbps. Then there are communication cost and computation cost. Now, if this data is cached in memory, let's say we have around 100 gigabytes of memory per machine, and this complete data is cached in memory, the reading cost or the I/O bandwidth of the I/O cost of reading this data from memory goes down by probably 2 orders of magnitude. Memory bandwidths are somewhere around 10 to 20 Gbps, but there are still computational costs, there are still communication costs, and even reading this amount of data might take around tens of seconds. So all in all, we see these kind of queries on this magnitude of data taking around 1 to 5 minutes to compute. And in this design space, what we would really like to achieve is interactivity as to if we can actually achieve or process this query on 10 terabytes of data or this scale of data on these machines in milliseconds or seconds. And if we are doing this, we cannot even afford to scan this entire data at runtime. To this end, what we did, we essentially execute queries on samples of data instead of the full data. Now, what do I mean by query execution on samples? Let's say that we have a simple table that looks like this. It has 3 columns. In this case, let's say this table reports some metric. In this case, this metric is buffering ratio for each and every customers along with their locations, right? So now if I ask this question, what is the average buffering ratio in this table? Now, a traditional database would essentially scan this entire column of buffering ratio, calculate the exact answer, and return something like this to the user. What query execution on samples mean is that we can actually take a uniform sample from this original table. So this is our table. We took a uniform sample with a probability of 1 by 4. So each tuple was in the sample with this probability of 1 by 4. And we can ask this question on this table. So we compute the average on that table, and we get some approximate answer. Now this answer in itself is not good enough because it does not tell us as to how far is this approximate answer from the original answer. So for this answer to be useful, we actually have to associate some error bounds to this query, which is to say that, okay, I know with a certain confidence that my true answer lies within 0.19 plus minus 0.05. Now, if you actually get a bigger and bigger sample, you can get more and more accurate answer and with lesser and lesser error bar. So this is like pretty much statistics 101. Now, if we are talking about approximate query databases, what they essentially allow us is the smooth trade-off between speed and accuracy. So as we operate on bigger and bigger samples, the execution time, which is the x-axis in this graph, goes up. And the error goes down by some function. So if you're operating on very, very small samples, you would probably incur some higher error. And as you're operating on bigger and bigger samples, the time it takes to operate on the samples goes up, but the error goes down. All our traditional databases are at the far end of the spectrum. They always operate on the full data set and give the answers which are exact, also called with zero error. What BlinkDB is designed to work in is essentially this left-hand side of the spectrum, which is to say that we would like to maintain interactivity for the queries and then give answers based on whatever the corresponding approximations are with these error bounds. Oops. Okay. So here is another real-world example just to show you the magnitudes of error that we can get if we are operating on real-world data. So this is some data that we got from Facebook. This is some basic ad-click data. I'll not go in too much details about the query, but I mean just for intuition, this is calculating some 99 percentiles of some like fraction of ad clicks. And this data, as far as I remember, is around 20 terabytes in size. And the x-axis here is the fraction of full data on which we execute the query on. So 1 means that we are actually executing the full query query on the full data set. 10 to the minus 1 means we are using a 10% sample, 1% sample, and so on and so forth. So the first, and the y-axis here is the query response time. So as we are operating on different size data sets or different size samples, the query response time decreases by some function. Right, so first of all, this query execution time should not come as a surprise, because most of the time the execution or the time it takes to execute a query is IO bounded. So if you read 10 times less data, you take your query executes 10 times faster. What's really cool is if we look at the error bars that we get. So this is, again, a function that calculates the percentiles. So we would get different error bars for different functions or different queries. But look at the kind of magnitude of these errors that we are getting if we are operating on these samples. This says that I can actually get 10 times faster answer with 99.98% accuracy. Similarly, I can actually get 50 times faster answer with 99.93% accuracy. And most of these cases, I mean, if we are calculating ad clicks, we are calculating like some other things, we are doing root cause analysis, and there are lots of real world applications that can probably tolerate these kind of errors. And our human mind is actually designed to tolerate these errors. I mean, your car odometer has actually 0.2% error that's inbuilt. So, I mean, whenever you see the number of miles that your car has run, there is an implicit error that nobody cares about. Similarly, I mean, there is some error that's associated with weighing machines, there is error that's associated with the speedometers, and so on and so forth. So when we talk about this error has an amazing property. This error, this property, this statistical property essentially says that typically this error that we incur on these samples of data does not depend on the whole data size. It only depends on the sample size. If you think about it, it does not matter if today I am working on a 1 terabyte data set and tomorrow I am just suddenly working on 2 terabyte data set, day after tomorrow, or maybe after 6 months I am working on 100 terabytes of data set. It does not matter. I will get the same accuracy of answers by using the same size of sample. So if I am using a 1 gigabyte sample on 1 terabyte data set today, even if my data set doubles, I can still get the same accuracy by using the same 1 gigabyte sample, right? However, like all statistical results, there are a lot of conditions that apply. I mean, what should be the exact size of sample? What would be the representative sample from our original data? What about different data distributions? What about different queries? How do you create those samples and things like that? So pretty much the goal of my PhD, and more general, like the goal of this system, like BlinkDB, is essentially to abstract away all the details from the user. So from the point of view of the user, what BlinkDB provides is an interface that takes in a query, a SQL query such as this, and allows the user to add a time bound to this query. The user does not have to worry about what are the kind of samples, what should be the size of samples, if the data distribution changes, how do you reconstruct the samples, and so on and so forth. Just provide a SQL query and allow the user to add a time bound to this query. Now, depending on this time bound, BlinkDB would give an approximate answer with some error bound. Now, if the user is not satisfied with this accuracy or the error, he can always increase the time it takes to execute the query, depending on which you can get a more accurate answer with a smaller error bound. We support a fairly large subset of the SQL standard, which is, I mean, we basically can support aggregates or approximate aggregates, which are of the form of average, count, sum, standard deviation, percentiles, like pretty much all kind of like standard aggregates that you can have. We support various filters or group by clauses in the query. We also support joins. More specifically, we support foreign key joins. We also support a fair amount of nested queries in the system. And last but not the least, we also support user-defined functions or ML primitives. So you can actually have k-means, or you can have like logistic regression, which you can potentially approximate using the system. Finally, we also allow the user to add an error bound to the query, which is to say that the user can now specify some accuracy that he wants the answer for. And based on this, BlinkDB would return the fastest possible answer that satisfies those accuracy criteria. Okay? So what is BlinkDB? BlinkDB is a data processing framework that is being built on Spark. First of all, what it does is it creates and maintains a variety of uniform and stratified samples on the underlying data. Uniform samples are those samples in which you sample the data with equal probability or with like uniform probability throughout. Stratified samples are those samples in which you sample different portions of the data with different probabilities depending on whatever you're interested in more. Second, it returns fast and approximate answers with error bars by executing these queries on samples of data. And last but not the least, the most important part of the system is it always verifies the correctness of the error bars that it returns at runtime. I mean, an approximate query database that sometimes can return wrong answers would pretty much be useless. So one of the key aspects of our system is actually this verification step, which is to say that whenever we return an error bar, we are confident that this error bar is good enough. And if it is not, I mean, there are a lot of queries which cannot be approximated due to certain reasons, maybe because of the nature of the underlying data, or maybe what you are trying to compute, and so on and so forth. We explicitly return that to the user and fall back to the exact computation. Okay, so I'll give a very brief introduction of each of these aspects of the system, and feel free to ask me any technical details further if you want. So first of all, creating uniform and stratified samples. So how do we do that is essentially we allow the user to essentially have a uniform sampling operator anywhere in the query graph. So let's say that this is a simple query graph. We can seamlessly allow users to add a uniform sampling operator in this query graph. What this uniform sampling operator does is it takes a query such as this, and then whenever it takes the data such as this, and whenever this is fed into the uniform sampling operator, it essentially filters with a uniform probability each and every row. Then it adds some per row weights to the column. So this is something that a weight or a filtering ratio is associated with every row of the database, which then is shuffled in memory. So this shuffling is done so that if you create a sample which looks like this, in this case the sampling ratio was 1/3, and essentially if you are shuffling this in memory, any subset of the sample is also a uniform sample. So this allows us to get a smooth trade-off between speed and accuracy. And last but not the least, it does not change any Spark RDD semantics. So the last column, which is the weight column, is completely transparent to all the queries. But all it does is it basically calculates the error, or in some cases, it scales back the answer to the right quantity. So let's say, for example, if you're calculating a sum on a sample, and if it's a 50% sample, you would want the sum to be scaled back to twice the required answer. So this all happens under the hood. Finally, we also support stratified samples, as I mentioned. Stratified samples are those samples in which you sample different portions of the data with different probabilities. So the stratified sampling operator is essentially a relational operator in the query graph. Whenever it's inserted, and it takes a data such as this, what it requires is a column on which you want to stratify on. And the way it works is, first of all, the stratified sampling operator inserts a split operator in the query graph. So whatever your data stream is, it is logically split across two streams. On one of the streams, you actually compute a summary of the input data set. So in this case, a simple summary could be just keeping track of the counts of NYC and Berkeley that appears in my original data set. Now, depending on the summary, you can actually associate a sampling ratio. And again, there could be different logic that could be plugged in that decides the sampling ratio. In this example, I have just taken a simple logic that essentially tries to keep the number of entities of both NYC and Berkeley same or similar in both in the final sample. So in this case, I'll pick 2 of NYC entries and 2 of Berkeley entries in the final sample. Once this is done, this sample or this summary and this entire table is joined on the city column or on the column on which you are stratifying the sample. And finally, you get something like that. You get a per row weight that's associated with the column by inserting the uniform sampling operator. And then you essentially get 2 quantities of NYC and 2 quantities of Berkeley, depending on whatever your sampling ratio was. So you join these 2 tables. The ratio of 2/7 was associated with all the tuples of NYC. The ratio of 2/5 is associated with all the all the entities of Berkeley. And when you join these 2 tables, you essentially get this kind of sample. And once again, this does not change any Spark RDD semantics, which means that you can actually just feed this table or this sample table in any part of the query graph, and the ratio or the weights would essentially take care of all the scaling and error calculations under the hood. Second, we return, as I mentioned, fast and approximate answers with error bars by executing these queries on samples of data. Now, technically, how this is done is, it is in 2 ways. First of all, we have something called closed form aggregation functions. These functions are of the form of average, count, sum, variance, and standard deviation. And how do you approximate this error is using pretty much standard statistics of central limit theorem. Now, what central limit theorem tells us is that the error that's incurred for each of these aggregates is some function, is some mathematical function. I will not go too much into the details of how these formulas are derived, but they are like pretty much standard statistical results that says that the error in the count is depending on the number, the size of the sample and the probability of the sampling ratio. The sum error is dependent on the size of the sample, the sampling ratio, sigma is the variance, sigma squared is the variance, and so on and so forth. Mu is the mean. So all in all, I mean, you look at the sample, you compute or you plug in some like the properties of that sample in these formulas, and you get the error. So for closed form aggregate functions, a simple implementation in case of BlinkDB would be just to modify these aggregate functions, which are of the form average, sum, count, standard deviation, and variance, and we allow this aggregate functions now to return that answer and that corresponding error by just modifying the aggregate function that now computes the error that's associated with the sample. Oh, sorry. Hello? Yeah. So now, if you're talking about generalized aggregate functions, so functions that are not of the form of average, count, sum, and all these kind of things, what we can use is essentially statistical bootstrap. And again, bootstrap is a well-known statistical results that is applicable to any complex and nested SQL query. It can be applicable to user-defined functions, queries that have joins, and so on and so forth. Right? So how bootstrap works, I'll just give an intuition. If we have a query that looks like this, so it is a sample, you execute a query on this sample, you get an answer. If you want to compute the error, you essentially take the sample, you insert the resampling operator in the query graph, and based on this resampling operator, what this does is it essentially creates samples of the same size with replacement. So multiple samples, let's say 100 of them with replacement, and executes the query parallelly on each of these resampled data. And the intuition behind this is that if you do that, you can essentially predict the distribution of the underlying data by using just the samples. Right? So based on this, we essentially get A1 to A100, which are like different point estimates that we got by executing these queries on repeated subsamples. And then we can insert it into a bootstrap operator that just tries to compute the error that's associated with any aggregate function. So again, like machine learning primitives, user-defined functions, queries with joins, queries that are nested, and other kind of like really complex structures can all be approximated using these techniques. And finally, we verify the correctness of error bars that it returns at runtime. And this is, again, like I'll give a very, very brief intuition of what it does, because this is something that is like, that is a statistical problem that we had solved like probably like in an year or two. And the key intuition or the key intuition behind the workings of this method is essentially we would like to figure out if on a particular sample size we return some error to the user, whether this error is correct or not. And the way we do it is we essentially try to figure out what is the error by executing the queries on very, very small samples of data and then extrapolating the upper and the lower bounds of the corresponding error that it would incur on bigger samples of data. And if the error falls within those bounds, we would say that yes, it is an accurate error. But if not, we would basically return to the user as to that this is not an accurate error, and we would fall back to an exact method or increase the sample size. So either of the two is possible depending on the condition. Again, like I will not go too much into the statistical details, but one of the more intuitive things is that if you use more data here, you get higher accuracy of predictions. And we showed in like some of the past research that if you get around 300 of these data points, you can be fairly accurate, like 97% accurate, that the error bars that you return are good enough or are actually like correct. Okay, so just to give a kind of like concluding overview, the first process, which is basically the sample creation process, is completely offline. So once some data comes into the system, we create these bunch of samples depending on whatever query distribution is, whatever the kind of data is there in the system, and this is an offline process. The second part of it is an online process. So the error estimation and the verification, all these things happen when a query comes into the system. So the first part can essentially takes